For any exponential function, like a to the x to any base a, the slopes will always be proportional to the y values. In a previous video, we said without justification that the proportionality constant will always be the natural log of a, the base a. Well, this is climb time, and in this video, we are actually going to justify why the proportionality constant has to be the natural log of a using the chain rule. All right, well, like I just mentioned, we have an exponential function here, base a to the x, and for any exponential function, the slope of the tangent line will be proportional to the y value. That means that as the slope gets bigger, the y value gets bigger. And if the slope gets twice as big, then the y value will be twice as big. If the slope gets 3 times as big, the y value will be 3 times as big. And so the proportionality constant is what connects the two together, and it is the natural log of a. So let's show why that's true. But first, we need to look a little bit at logarithms and how they work. So let's say we have y is equal to a to the x. All right, so that is our function. And we want to look at how to change the base. So we have a change base formula, but I want to show you where the change of base formula comes from. So the way we get a variable out of the exponent is we take the natural log of both sides. So if I take the natural log of both sides, like such, the reason why that's useful, and you can take the natural log of both sides equation, that's perfectly allowed. The reason why that's useful is we can take that x now and move it to the front of the natural log. So on the left, I have the ln of y, and on the right, I have x times the ln of a. And so now the x is no longer an exponent. And this is using the property of logarithms with powers or exponents. And that's because logarithms are kind of unique in terms of how multiplication and addition works together. You can sort of transform multiplication and addition and vice versa with logarithms because of their unique properties. So one of the things we can do because of that is we can take an exponent. If we're taking a log of any base, of something raised to an exponent, we can move that exponent to the front. So now the variable x is no longer an exponent. Now, the way we get rid of a natural log, because we really want y, we're looking for y again, is we can exponentiate both sides. So if I exponentiate both sides, what that means is basically using the same base, I raise the left side and make it the power to base e, and I take the right side and make the power the same base e. That is perfectly allowed as well. So if ln of y is equal to x times the ln of a, then e raised to the ln of y is going to equal to e raised to x times the ln of a. Perfectly allowed, perfectly okay. And the reason why we want to do that is because e, the natural base, and ln, which is log base e, natural base, they cancel each other out. They're inverses of each other. They undo each other. So when you take a function and you compose it with its inverse, so the internal function, as I like to call it, the internal function, is the inverse of the outer function, or it is the first function in the chain, and this is the second function in the chain. They undo each other, and that's why we're doing this. So then you end up with y on the left, and on the right, you have e raised to the x times the ln of a. Now, the reason why I'm doing this is change a base formula. So this is a way to change an exponential function from base a to base e. Same exact function, goes up the exact same rate. We're just sort of moving around some things that make it helpful for us when we're finding the derivative. So instead of base a, it's now base e. Instead of raised to x, it's raised to x times ln of a. All right, so now let's take a look and see what happens when we try to find the derivative. So if y is equal to e raised to the x times the ln of a, I can see that this is a function within a function. This is a chain rule situation. And I'm going to go ahead and show more steps than I might normally show, just to make it obvious what's happening here. So I'm going to make the internal function, my u, I'm going to call that x times the ln of a. And so that means y becomes e to the u. And so now I know how to find the derivative of e to the u. It's just going to be e to the u. So dy over du is just e to the u. And then the derivative of u over here is going to be du over dx. And I'm actually showing more steps than I need to here. So the derivative of x times the ln of a is going to be just the ln of a, because ln of a, we're assuming a is a number, it's a constant. And so therefore, this is just a constant. So this is just some number times x. And so the derivative of some number times x is that number, ln of a. All right, and so I'm kind of showing my steps on the chain rule here. Probably don't need to do all of that because we've learned how to do chain rule already, but I am showing my steps in the chain rule. If I want dy over dx, which is the original derivative, that means the du has to move over here. I have to divide both sides by dx, so I get dy over dx. By the way, check out my other video on why the chain rule is true, which basically I'm showing you why as well right here. And that'll give you just a little bit more information, more details on that. So this becomes e to the u times du over dx. And this is why the chain rule is true, is that this du can move over to the other side, and then divide both sides by dx. So dy over dx, which is my original derivative, is equal to e to whatever the input is, times the derivative of the input. And so the derivative of the input, u, which is x times L of a, is L of a. And so we end up with dy over dx is equal to d over dx is L of a, and then times e to the u. I'm going to go ahead and plug back in for u, so that's x times L of a. And so we already see kind of what we were trying to set out to show. That's why the proportionality constant L of a, it's right there. Maybe I'll put it in a form we're more familiar with. We know e raised to the x times L of a. That's the same thing as a to the x. So I'll go ahead and put a to the x back in there. So we see dy over dx is equal to the ln of a times a to the x. And that's what we were setting out to show. We're setting out to show why when the slopes are proportional to the y values, why the proportionality constant comes out to be the ln of a. And the reason why is because of the change of base formula, basically. The change of base formula, which we can get by just exercising the property of logarithms and the fact that e and ln cancel each other out. And then using the chain rule here, we can see that dy of dx, which is the slopes. So this would be slopes here. That's the slopes group. And then this is the y values right here. Y values. And so then this right here is going to be our proportionality constant, which we might call k. So slopes are equal to some constant k times their y values. So this is why this is the formula why if f of x equals a to the x, then f prime of x is going to equal ln a times a to the x. It comes from the chain rule and also comes from the property of logarithms and the change of base formula. Well, the change of base formula comes from the property of logarithms and then the chain rule. You put those two together, then you see why ln of a comes out as the proportionality constant between the slopes and the y values.